Wait, okay. All right, okay. Welcome everyone to our seminar. Our visitor, Dr. Mark Cheung. This is probably the first in-person seminar in a very long time. So we're very happy to have about 10 people in our room, just below the quarantine limit. So Mark Cheung is a staff physicist at the Lockheed Martin Solar and Astrophysics Lab. He's the PI of the atmospheric imaging assembly instrument on board the NASA's Solar Dynamics Observatory. And he has worked on a broad range of different science topics, including numerical simulation of the solar atmosphere and the machine learning topics that he will talk to us today. So without further ado, Mark, please go ahead.
Thank you, Sudong.
All right, thank you, Sudong. Can you hear me? Can people hear me? Okay. Yes, it's a privilege to visit IfA Maui again and to give this presentation. Today, I would like to talk a bit about machine learning in heliophysics. And I will give a brief introduction about heliophysics and about machine learning because we have a fairly widely diverse audience. So please bear with me if you know a lot of the first few slides already. But also feel free to stop me at any time. If you do ask a question, if you post it in the text, probably I ask Sudong to monitor, or if you want to say something, I will repeat your question because I'm the only one who could hear you because the speakers are not on. Okay, now with that, let's go forward. So for those of you who are new to heliophysics, heliophysics is first and foremost at the beginning a division of NASA Science Mission Directorate, and it's become a discipline that integrates many of the traditional subdisciplines in solar physics, space physics, astronomy, magnetospheric physics, space weather, climate, dynamos, even some of planetary exploration and astrophysics and more. And the distinction between heliophysics and astrophysics has always been blurry, and the distinction between heliophysics and planetary physics and astrophysics becomes blurrier as more and more people realize that a lot about what we study about the sun is relevant for understanding other stars, as well as for understanding the planets around other stars. So it's getting more and more attention. At the same time, it's getting a lot of attention from various stakeholders in the country and internationally because people are starting to be aware that some space weather effects could have the potential to disrupt technologically dependent life, including power grids, including radio communications, including the effect on satellites, but also on astronauts. So heliophysics is becoming a more and more important discipline, and the term is starting to be used more and more. NASA has a so-called heliophysics system observatory, which is a fleet of spacecraft that are in different orbits, some of them around the Earth, some of them around the Sun, that are monitoring different aspects, including how the magnetosphere of the Earth changes, including how the ionosphere changes, including how the Sun changes, and also including the solar wind. Okay, so that's heliophysics. Now let's talk about the other side of the talk, that is machine learning. And I should first of all say that I'm by no means an expert in machine learning. There are people whose whole careers are in machine learning, and machine learning is growing at such a fast rate in terms of the literature that most of these people are also becoming just experts in the subfields. But nevertheless, in order to start the the presentation, I have to explain a little bit about generally what people mean by machine learning. Okay, so, all right, forget about the last bullet point there. There are generally, for starters, 3 types that people talk about. That is supervised learning. So in supervised learning, you have an input X, you have an output Y. So X can be some measurement vector, Y can be some classification, or it could be some quantity that you want to regress. Maybe you're measuring the Stokes parameters. You have some spectra and polarization, and you want to find out what is the magnetic field on the surface of the sun. That's one example. So there's a lot of workflows where you take this input data X and you want to find out what is Y. So you're trying to find the mapping. You're trying to learn the mapping from X to Y. In other words, you can also phrase it in terms of probability distributions. It will be finding the conditional probability of Y given X, or the likelihood. Okay, so if it's discrete Y, then it's classification. If it's continuous Y, it's regression. Okay, there's unsupervised learning. That is, you don't necessarily have an output Y, but you have collected all these measurements, and maybe you want to do you want to understand how the data is structured. One way you do that might be to build a histogram. You collect some data, build a histogram. That's inferring the probability distribution of X. So maybe your data is clustered in a certain way in n-dimensional space. Maybe the dimensionality is less than n. So unsupervised learning can be broadly summarized as trying to infer the probability distribution of X. Okay, so these 2 types are introduced in this textbook. A lot of the machine learning work has a lot of heritage from statistical learning. A lot of statisticians have been working on this. Applied mathematicians, statisticians have been working on this for a long time, even before it's become very, very hot. It's become very, very hot and popular because things started to work at scale in recent years. But it's not a new thing. Okay, so there is reinforcement learning, which typically is considered a different branch of machine learning. And that is, here you have an agent embedded in an environment. The agent senses the environment in terms of different stimuli. For example, you might have, your agent might be a driver, and it gets to see the scene. The scene can be rendered from a simulator. And then its goal is to maximize some reward over long term, or over some time frame. Okay, and the agent has its own state. The environment has its own state. The agent has some policies to decide what actions to take. The actions might affect the environment. If you're crashing into another car, that might affect the environment. So the goal is to maximize the cumulative reward. The first 2 types of machine learning have been used in heliophysics. So far, I'm not aware of reinforcement learning being used for heliophysics, but you can well imagine that if you want to have autonomous planning of some solar observations, maybe you can have it do that too. Okay. In all of these applications of machine learning, there are some very important considerations. Okay, so let's say you're doing supervised learning, and you want to learn the mapping from Y to X. You have to choose between how you split the data between the training, validation, and testing sets. Forget about validation for now. That's usually used for deep learning. But if you have training data and testing data, and you train your model to overfit the training data, it will do poorly on the testing data. So So you have to be careful. One way to overfit your data is, for example, in your training data, you have a regime, you don't go to all the corner cases, and you're fitting only a very local area. And then as you apply your trained algorithm to let's say classify the test data, you just get it all wrong. So ideally, you want your training data and the testing data to be sampled from comparable distributions, but it's not always possible. It might not be possible in practice, maybe because you're trying to predict solar flares, and first of all, we're not sure that the active regions in this solar cycle might have the same properties as the past solar cycle. Therefore, it depends on the input parameters you use. It's important though that you don't want to fool yourself into overfitting and think that your model will do well later. So, for example, some flare prediction models might be trained on different flares, and the flares from the same active region might be in the test set and the training set. So it could be that you've already in the training set seen this active region, you know there's flare, and so when you now show an image of this active region, if it's although it may be a slightly different time, it will just classify it as a flare productive. So you might fool yourself if you did that, but it depends highly on your purpose. If your aim is to go forward in time, and then you've seen that this active region has just produced a flare, then it's actually a pretty good predictor that it might flare. So maybe that's what you want. So all these decisions depend highly on your aim. There's the consideration about pre-processing. A lot of the machine learning practitioners, especially those working with computer vision, the first thing they do is they take the data set and they standardize it by subtracting the mean and dividing by the standard deviation. But that might not make sense for the scientific data that we have. Maybe the scientific data that we have is not normally distributed. Maybe it has a power law. You might need to log scale it, for example. And there are some examples of that later. Okay, so when you train a neural network, for example, you choose a penalty or a loss function. So what do you use? That again depends on what you want to do. So the recommendation is not to do these machine learning projects in the absence of subject matter experts. A lot of times, someone might discover that something works really well, but then once they talk to the subject matter experts, then it's obvious that it works well because of this reason, or it's trivial, or that they're discovering some they're rediscovering some known anomalies in the data. So it's better to do it together with the subject matter experts. Okay, so what can ML do for heliophysics? So we can do some accelerated analytics. For example, maybe you can do Stokes inversions quickly. And I think there's a project here that Sudong is leading that is doing that. You could do pattern discovery. For example, in unsupervised learning, you can discover the structure of the data in your n-dimensional space. But also, even if you're doing classification, for example, flare classification, if you have a predict flares, then the different layers of if you have convolutional layers, the different layers of the convolution, the different convolutional layers might be trained to successively pick out certain features in the image, like straight lines and then combinations of straight lines. Did I lose my AirPod? Can you still hear me? No, I think it's fine. Okay. Maybe we can do smart resource utilization. For example, with reinforcement learning, you can plan your observations better because you can do some things faster with machine learning, like with inversions. Maybe you can do like Stokes inversions on board a spacecraft and save telemetry. And because you can do it fast compared to solving the full radiative transfer inversion problem, you save power. Okay, power is a major constraint on space missions usually. Maybe you can do dimensionality reduction. You might be able to, given that there's a finite mass you can send up into space, or given just basically design constraints, even if it's a ground-based telescope, maybe you can enhance the observational capabilities. Maybe you can denoise your data, for example. You could potentially do data augmentation. So you learn the distribution of the data, and then you can generate synthetic samples. Okay, you can deploy deep neural networks in deep space and have more autonomous missions. Those are possibilities. Okay, so the useful types of skill sets that are needed for machine learning. Actually, a lot of people don't use all of this. It's useful, first of all, to be familiar with NumPy. Of course, I think any astronomical data analysis with Python cannot avoid NumPy anyway. But then you might also want to be familiar with number, because it's another way to make the Python code run very fast because it's compiled. Sometimes you have a lot of data that you have to work with. You can use stacks to do your data processing, pre-processing over many machines, over entire clusters. For learning to do machine learning, there is Scikit-Learn, sklearn. I'll talk about it a little bit more. And then for deep learning, there's TensorFlow, PyTorch, JAX. I haven't used Julia, but some people use Julia. And then there's a lot of scientific programming that we can do with the GPU these days that is relatively simple. And you can use CUDA, or it should be CuPy. I don't know what happened with the Y. It's becoming easier and easier to use the GPU for general purpose programming. And then because a lot of the code base out there is on GitHub or GitLab, it's also useful to be familiar with Git. So I would consider many of these to be desirable skills for a new postdoc or PhD student to have, not just for the sake of doing heliophysics, but in terms of general employability in the industry. Okay, so you can start playing around with things very quickly. You can start using GPUs without having your own GPU by, if you just go to colab.research.google.com, you can start a Jupyter notebook. And the default is to use it will have just a CPU, but you can choose a GPU instance that would have a fairly powerful GPU. And the free version of this type of Jupyter notebook sort of dies if you are leaving it idle for a few minutes or tens of minutes. But if you pay $10 a month, the sessions last longer. It's relatively inexpensive. Of course, you can also become a cloud computing platform, a customer, and then you can set everything up yourself. But just for starters, this is really quick to start. And then there is a neat trick that the Google Cloud or Google AI people use, apparently. I learned from one of the people at Google Cloud, is that if you have a GitHub repo that has a Jupyter notebook, you can just change the beginning of that URL, replace it with colab.research.google.com/github, and then the rest of that GitHub URL with the Jupyter notebook, and it will automatically load that Jupyter notebook into your Colab session, and you can start playing around. It assumes that the packages are installed, and AIAPy is installed already. I mean, AstroPy is installed already on Colab as a default. SunPy, you just have to type one command to install it and restart the session. But all the Scikit-learn, all the NumPy stuff, that's all pre-installed. So it's pretty good to start. SunPy, I have so many typos in these few slides. I am sorry. Okay, if you haven't done any machine learning, Scikit-learn is a good way to start. Can you still hear me? My earphones are telling me that it's sort of dying. Can you still hear me?
Oh, good. I can hear you.
Okay, good. All right. If you haven't done any machine learning in Python, Scikit-learn is a good place to start because there is this roadmap. So suppose you have some data and you ask yourself, are there enough samples? You follow the roadmap. If you don't have enough samples, it encourages you to get more data. And then are you trying to predict a category? And then it asks you, do you have enough do you have label data? Or are you trying to predict a quantity? So classification or regression. If you don't have label data, then you're doing clustering. So this is essentially unsupervised learning. Maybe you're just playing around, looking at the structure of the data. You're trying to do perhaps dimensionality reduction. So it tells you which algorithms you might want for the type of thing you want to do. And it's already very powerful. And there's a lot of problems that don't require deep learning that can do very well with the algorithms in Scikit-learn already. For quite a long time, I think a lot of the Kaggle competitions were one, not using some deep learning models, but with gradient boost, things that you could find in Scikit-learn. And the important thing is that the way you set up the whole problem of partitioning your data into training and testing sets, of doing something like cross-validation, all that way of thinking has been already sort of formulated in the typical Scikit-learn workflows. And so after you've done that in Scikit-learn, going to a deep neural network is quite simple, and it just fits that type of thinking and workflow. Okay, so it's very useful to learn. Okay, so now onto some machine learning cases. We won't have time to cover all the. There's also a bonus case and another bonus case, but we try to go into some example cases. There's a lot of. Okay, so first of all, there's more and more work being published, so one cannot give a review. Hello? Someone was trying to say something. Okay, so first of all, there's so much work on machine learning in heliophysics that one cannot do justice to all the work that's being done, and a lot of these case studies are the cases that I'm most familiar with. So it's a very biased view. A lot of it has to do with remote sensing, but there's also people doing machine learning on in situ data on particle distributions, for example, coming out of Goddard. A lot of the work has also received criticism that is very far away from the physics. That's you just trying to fit something and you don't learn any insight into it. But we can start to motivate machine learning with a simple physics-based problem, and that is photospheric magnetic field evolution. Okay, so with the Solar Dynamics Observatory Helioseismic and Magnetic Imager, HMI, we can observe how active regions on the sun evolve. You can measure the magnetic field that evolves, and you see that there are black and white patches. These are magnetic polarities of opposite sign, magnetic field coming out of the sun and into the sun. Okay, so because magnetic fields are in bundles, they are usually paired together. So there's a lot of dynamics. Every active region looks different. The way these things evolve, the way they emerge and and move about on the surface of the sun determines how the magnetic field above is structured, how it's energized, and whether it will tend to flare or give an eruption. So we want to follow how the magnetic field evolves. Often in the past, what people do is they take an image like this, and then they segment it into different patches using some image segmentation algorithm. They repeat the same thing with the next magnetogram, and then they try to identify which ones are the same patches and how they move, and they try to follow the flows that way. Okay, that's fine, but what if you wanted to know from pixel to pixel how the magnetic field is moving? What if you wanted to know the fluxes of the magnetic flux across your pixels? We'll get to why we want to do that later. So how do you track magnetic flux transfer on the solar surface? So let's do a thought experiment. Suppose you have a running difference magnetogram. That is, the magnetogram taken at this time and then the next time, and you find out the difference. So if your running difference magnetogram looks like this, one pixel has gained some magnetic flux, the neighboring pixel has lost some magnetic flux. You probably expect maybe the black pixel had some flux and it moved to the left, so the neighboring pixel gained some flux. So there's a plus in one pixel and negative in another pixel. So that's one explanation of what might have happened. Okay. You can also have another explanation, that is you have some loop that emerged, and so one polarity has positive, polarity has negative. That's also a plausible explanation. Another plausible explanation is that you have a submergence of a U-shaped loop. It will give you the same running difference magnetogram. Okay, the leftward motion of a positive one I already mentioned. You can have the rightward motion of a negative flux element. All these four scenarios will give you the same running difference magnetogram. Okay, but also a linear combination of all these would also give you the same running difference magnetogram. But actually, the important thing is that when you look at the electric field, so when we think about heliophysics, especially on the sun, when we think about magnetohydrodynamics, the electric field is typically the most important contribution to the electric field is the minus velocity of the plasma cross the magnetic field, B. So minus V cross B. That's got to do with how the magnetic field is being affected by the plasma flows. Okay, that's the major contributor to the electric field on the sun. In all these four cases, the electric field between these two pixels is the same. Why do we care about the electric field at these boundaries between pixels? Because the curl of the electric field over any surface tells you how much the magnetic field is changing. It's just Faraday's law. So we want to know the electric fields of all the pixel boundaries such that the curls explain how the magnetic flux is changing. Okay, but in all these four cases, it's actually the same numerical value of the total electric field. It might have contributions from vertical flows and horizontal flows, but the net is the same. Okay, so there's this scenario. Okay, there's another scenario. What if the positive and the negative in this running difference magnetogram was separated by a blank pixel? So you can think, oh, maybe you have a loop that's just emerged, or a loop that's submerged, and then you can have leftward or rightward motion. But maybe your magnetogram cadence, you didn't take enough snapshots, so they've now separated a little bit. But again, the numerical value of the electric fields in these two lines, the green lines, are the same in all four cases. Okay, fine. This is what we plausibly think when we're thinking about the electric field due to plasma shuffling the magnetic field. If you're thinking of the electric field in your standard undergraduate EM course, the electric field is space filling usually.
in in a laboratory environment or around atoms, whatever. In magnetohydrodynamics, we think of the electric field as mainly due to V cross B, because the magnetic diffusivity is low. It's mostly ideal evolution. And then you can say that where there is no magnetic field, because E is minus V cross B, the electric field also should be small. So we think that the electric field should be compact in space if the magnetic field is also compact into different patches. So that's the physical, this is subject matter experts' input into this, that the electric field is not everywhere. Okay, in this other scenario, you have some positive change in the pixel just somewhere. But what caused this, okay? Again, it could be just your field of view didn't capture the other polarity, or this thing just moved in from the side boundary, okay? All the same. All the same. So the electric field, we think, you can see the green there, yeah, okay. All right. So those are the plausible solutions to the electric field. But now, how do we capture this intuition into mathematics? The problem is that, okay, so let me say, okay, yeah. You have here, let's say nx by ny pixels in your running difference magnetogram, but you want the electric field in both horizontal components, so you almost have twice the number of unknowns as your knowns. Okay, so you have an underdetermined problem. You want an electric field that explains how the magnetogram evolves. You basically want the circulation of those electric fields to be the running difference magnetogram in all the pixels. You can write the circulation using finite difference as an operator A working on your electric field X, and that is equal to the change in your magnetic flux in each pixel. So it's a linear system. Okay, so you have an underdetermined problem. Now, but even though it's underdetermined, not all solutions are preferred. You want a solution such that the electric field is compact. Okay. You want a compact. Because if it's ideal, it's linear in B. If it's diffusive, it's also linear in B. Okay. Okay, this is assuming that you're not averaging in time so much or having so low cadence that your turbulent correlations make the electric field space filling. Anyway, when you seek a solution, you can then say, how about the solution you want is the one that minimizes this quantity here. So this was introduced by Yates in 2017 when he looked at surface maps of the sun. Okay, what this does is that you're trying to have AX equal to B as much as possible. That's just trying to explain your data. But you also want to penalize it by saying that you want to have a electric field only where you need it. So that's the regularization term. When you do this, what you end up with is exactly the solutions that I showed before, those green lines, actually. So Scikitlearn has exactly an optimization routine for doing this. In a sense, what you're trying to do is trying to minimize the amounts of things that you have to move around, shuffle around on the board in order to explain the difference. This is the problem you're solving. So when you use the Scikitlearn lasso routine for this running difference magnetogram, you get this electric field. For this particular case, you get this electric field. Okay, and then you can apply it to the sun. So suppose you only see the front of the sun, and we only see the front of the sun in terms of magnetic field usually. You have an active region that is moving across the horizon, across the limb of the sun. And you only see the leading polarity of the sun. In a lot of methods, that they build the magnetograms, synoptic magnetograms, they have the problem that they will suddenly have a magnetic map of the sun that has a non-zero divergence. So you're breaking the laws of physics because suddenly there's more flux. But that's just because you're not seeing the backside. The way to do it is to say, this is your running difference magnetogram in this limited field of view. Solve for the electric field. And after you've solved for the electric field, then at the edge where a new polarity has come in, that electric field would be such that when you take the curl on the other side of what you see, it will create the balancing magnetic field, and then you will not break the divergence B constraint. So that will mean that when you use this map and do a potential field extrapolation of the sun, suddenly you don't change the topology of your field because it's only local changes. So so you can take the sequences of front side maps from HMI, and then you can keep on updating your magnetogram over the whole force pi steradian by using these electric fields, and the divergence of B over this frame, over this surface will always be 0 by construction. Okay, so that's one way to, I am going to plug in my power supply. 1 second. Okay. So that's one way to apply machine learning in the broad sense that you're using all the methods that have been developed for optimization to solve a physics frame problem. Okay. All right. There are other ways to use that type of technique. So suppose you want to look at temperature diagnostics of the solar corona. We have all these images from the Solar Dynamics Observatory in the extreme ultraviolet channels. Each one, I'm just going to go with it. Each channel is actually sensitive to plasma over a range of temperatures, just because you code your mirrors, and there is a finite wavelength bandwidth, and inside that bandwidth, there are different spectral lines that are sensitive to different plasmas. So different channels of AIA are sensitive to different temperatures. Typically, we would use like 6 channels of AIA, and we want to get maps of how much stuff there is at different temperature bins, but we want more than 6 temperature bins. So again, it's the same underdetermined problem. And if you're thinking about optically thin radiative transfer, then it's just a linear problem again. So you apply the same technique. Okay, so you have, in a stack of images, for each pixel, you have 6 AIA channels. You have the count rates. You want to solve for a vector that is longer. That is how much stuff there is in each temperature bin. That each component is basically the electron density squared in that temperature bin. And then you have this matrix, okay? So your constraint is that the components of Y must be non-negative, because NE squared has to be non-negative. But you also probably want to use the least amount of emission measure. So NE squared integrated over the line of sight is the emission measure. You want to use the least amount of emission measure to explain your signal. You want some sparsity. You don't necessarily want continuity from one temperature bin to another, because when you look through a pixel, there might be just one coronal loop that is one temperature, and then further away, some coronal loop at a different temperature. There's no reason why there should be continuous, smooth distribution in temperature space. Some people impose that constraint for the inversions, but you don't have to. So when you try to minimize the problem like before, actually, it's not exactly posed as the same before. Here, we're just saying we minimize the emission measure needed. We minimize the Y, the L1 norm of Y needed to explain the signal. Then what you end up with is these maps. So this is scanning in temperature space in log T. And this shows you how much emission measure, or the line of sight integral of the density squared is in each temperature bin. Okay, so you can do that with AIA. And then you can say, okay, you have this solution now for how much stuff there is at different temperatures. And can you predict what the X-ray image would look like? So AIA is using extreme UV, but there are other telescopes that measure in X-rays, and you can. So the top left here is an X-ray image from Hinode XRT. The panel next to it is the predicted image from AIA. And then for the bottom row is also XRT and synthetic, but for a different channel. So that tells you a few things. Is that oh yeah, there's some reasonable solution that you're getting from this inversion because it predicts the X-ray well, and we didn't use the X-ray data at all. Also, just because you're looking at X-rays doesn't mean you're looking at hotter stuff than what you're seeing in extreme UV images. Often people say, okay, EUV is this temperature, X-ray is this temperature. It's not exactly true. Okay. By the way, this was not really machine learning or deep learning, some fancy deep learning. But recently, people are starting to use train the neural network to go directly from the AIA images to the X-ray images. So you're making your telescopes more capable. Okay, so I talked about how you can do a local minimization problem to get the differential emission measure just now, but that's sort of slow. Maybe we can train a neural network to do this so that we don't have to do this optimization problem every single pixel. Okay, so if you just took that data from the inversion and used it as training data for a deep neural network, and this is a very simple, fully connected network, nothing fancy. And you have these constraints. The inputs and the outputs are non-negative. Because of the high dynamic range, you apply square root scaling so that you can capture a wide dynamic range. And then in between the neural network layers, you have some nonlinearity function. Because we know that the output has to be non-negative, you can choose some activation function which ensures you don't get negative values. And ReLU is one of them. Okay. Anyway, if you do that and you have no hidden layers in your neural network, it doesn't do very well. The solid line is the differential emission measure summed up over the ground truth as a function of temperature. The green is the output from the neural network. It's not very good. You keep on adding layers and then it becomes better. Okay, but also the important thing is before we were limited to doing things at like 8,000 pixels per second. Of course, that was on a single CPU thread in IDL. It's not a very fair comparison. But once you've trained the neural network, you can just deploy the neural network on different GPUs, and then you get orders of magnitude increase in the throughput. So suddenly, something that took minutes now just is instantaneous. Or equivalently, you can also do this with much less power requirements in case you want to deploy it up there in space. There is a chapter of the HelioML electronic book by Barbara and Mason about how we train a deep neural network for these DEM inversions by Paul Wright et al. So you can find the link in the recording. Okay, this is a Jupyter notebook telling you how to do it from scratch using PyTorch. It turns out that the trained neural network actually has fewer artifacts than the original, which is quite amazing, and I don't think we understand yet. But it's not overfitting. Okay, to enable more people to do machine learning on the Solar Dynamics Observatory data, we released a machine learning data set. The problem with the SDL data is that it's petabytes of data. It's a lot of data, and even though it's pretty regular, it's sort of hard to use unless you have been in solar physics and trained to use the data set. So we've done a bunch of things. We've made sure that the images of the sun are the same size in terms of number of pixels throughout the year, it changes throughout the year because of the elliptic orbit of the Earth. The sun gets bigger and smaller. There are also some instrument degradation that we've corrected so that you don't have to correct it yourself. So everything is aligned. It also includes the Eve spectral irradiance data. So there's AIA, HMI, and Eve. Okay. So with that, one thing we did at the Frontier Development Lab was to say, okay, we have SDL data that has been observing the sun for many years. We have the images from HMI, we have the images from AIA, we have the spectra, the EUV spectra from Eve. But Eve, I can skip this slide. Eve measures the spectra integrated over the whole sun like this, the yellow line here, with the max A channel. There's some overlap with the AIA channels. Those are the tick marks at the bottom there. But because of an electrical anomaly in 2014, we no longer have this data from Eve. But we have 4 years of overlapping data from AIA and Eve. So could we try to generate a proxy Eve data with AIA images? Okay. So that's what the team did. We took the AIA data and then trained a model to predict what the Eve line irradiance signal would do. Okay. And actually, it's a fairly simple model. It turns out that if you just took the means and the standard deviations of the AIA images and fitted a linear model, you do pretty well already. So that's the bottom stream here through the red boxes. That's the linear model. But if you want to do better, then you can take the rest of the information and then go through a convolutional neural network. And because it's sort of a correction, it's what's called a residual convolutional neural network to do a better job. Another way to do it is, of course, you do your DEM inversion from AIA and then predict the Eve irradiances that way. But the machine learning model is outperforming the physics-based model. And it's not so surprising because we know there are some limitations with the physics-based model, especially the DEM assumptions are not good for the 304 channel, for example. Okay, all right. So these are just comparisons of different models. Once you have trained your neural network, you can then rearrange the components such that instead of predicting the full the irradiance summed up over the sun, you actually get the images of those individual spectral lines before you sum it up. So basically, the bottom panel, the top row shows the AIA images, and the bottom row shows the spectral line in irradiances over the sun, such that when you sum it up over the image, they become the Eve irradiances. Okay. You can also say, oh, you have a few AIA channels. Why don't we try to predict another one? Okay. You can sort of do that. And people have been doing a lot of this, not just with SDL data, of course. There's a paper here by, I think was it a student intern who took a Solar's helium 1 observations and mapped that to EUV and vice versa. So there's a lot of opportunity for this type of work. Okay. Now, none of these predictions are perfect. So whether they're good enough, again, depends on your purpose. It could be that you don't care about some spatial details and the net contrast or the image, the summed signal is enough for you. But if you care about the details, it might not be enough. Okay. I have no time. AIA suffers sensitivity degradation because different molecules can pop off the structures of the telescope and then deposit onto the mirrors. So it gets less and less sensitive with time. But we need to correct for it. And there's no standard EUV source, really. No standard candle. The problem is that over this time range of years when it's degrading, the sun is also changing. So how do you calibrate? The proper way to do it is to send a sounding rocket like the IfA team does that replicates the IfA instrument every few years, and then take the new data and then compare how IfA degrades and compare with AIA, and that's what we do. But you do it every few years. If you want to continuously monitor that, you have to use other methods, some proxies. Okay, so for example, these circles are the sounding rocket measurements. So one way we decided to try it out is to use the SDO-ML dataset. So remember, the SDO-ML dataset has been degraded, has been degradation corrected, and this has been degradation corrected throughout the whole mission. But the quality of the correction is worse after IfA is no longer working. But the quality of the correction before that time is good. So we have a good handle on that. So that's a data set that we can trust. Now, given that we trust the SDO-ML data set for the first few years has been correctly corrected, what can we do? We can generate a synthetic data set. We can artificially say, oh, this channel has suffered this value of degradation, alpha. This channel has suffered this value of degradation, alpha. And now, given this synthetic data set of alphas, we want to try to recover alpha. How do we do that? So suppose you give a model a stack of images. We know that the certain features on the sun, they correlated over different channels, like active regions, tend to be bright in multiple channels. So there must be some spatial correlations that you can use to learn this. Okay, so this is the team that did that. Yeah, anyway, they're a very cool team. We had Miho, who was a mentor also, together with me. We had, so she's a heliophysicist. We had Gunesh, who is a machine learning researcher at Oxford, who is the world's expert on auto grad methods. We had a machine learning engineer who was at Dropbox, and now is at Planet Lab. We had a cosmologist. We had also 2 PhD students in heliophysics. Then we had a machine learning professor at Oxford. But you need an interdisciplinary team in order to do this. So what we did was we had this, let's say, ground truth data set. And then now we generate a bunch of degraded images, okay? We just sample alpha between 0.1 and 1 and randomly, and then just degrade these images. So we know that, but we know the original ground truth, right? So what we need is then to have a model that given the images on the right, it has to find the alpha. That's what we need to do. Basically, what we're doing is, okay, in principle, the sun is changing, okay, and in alpha space, the true solution follows some curve in time. We don't know what this true curve is, but if we have enough training data such that we're covering this hypercube of alpha, then we should be able to recover this curve. And it's a very simple convolutional neural net, actually. You just give it a stack of images, it spits out the alphas. This itself wasn't very interesting. The interesting thing is you have to figure out a way to to sample the data in a way that you're not biased by the evolution of the sun. Okay. So with that, we've updated our calibration. So in a paper published this year in Astronomy and Astrophysics, there are the curves that come from the machine learning model. Okay, so to summarize, there are all these things that you can do for heliophysics. I want to shortly talk about some work that other people have done. people have been very ambitious in generating magnetograms from EUV images. And it's very strange for the solar physicists, right? Because the EUV signal or intensity in general should be invariant to the sign of the magnetic field. So how do you get the polarities? Well, I think it's because of the bias in the cycle of the data that they use, of course. And then some people might say, oh, if you compare the AI generated one and the HMI observation, it looks terrible. Okay, so you will not use this generated data to study the details of active regions, right? But maybe if you're interested in just the global topology of the connectivity of the field in a PFSS model, just having this might be enough for your purposes. So this is something that like people doing flux transfer models like Lisa Upton said. I mean, it's better to have this than to have the like wrong patches of polarity, large scale at all. So again, whether it's good enough depends on what you're interested in. Okay, people do accelerated inversions for spectra, and I'm sure people will be doing that with DKIST. People do flow tracking with convolutional networks, but there's other things, and this is not really being exploited as simulation on statistical learning methods and differential programming techniques that you can use to do posterior estimation, to do general function optimization. And there's a lot of physics-based problems, that could use these type of methods, but we're not exploiting them yet. Much of machine learning in heliophysics has been to map from one data to another, or to do something quicker. And then the deep learning frameworks themselves, they essentially like a NumPy supercharged. I mean, they're also much more capable because of the differentiable aspects, but they make using the GPU really, really easy. So you can write something that looks like NumPy, and then suddenly runs on the GPU and is 100 times faster. For example, radiative transfer calculations. So all these haven't been really exploited so much yet, but I'm hoping that they will be for heliophysics. So with that, I think I will stop here. Thanks for your attention. Are there questions? Maybe I can. Let's see. I don't even know whether my headphones are working well. Are there questions from the
Hi, Mark.
audience? Hello?
Hi, Mark. This is Tetsu.
Oh, hi, Anand-san. Yeah.
Hi. I have a question. Yeah, thank you for nice talk. And yeah, on ground-based telescope, seeing degraded solar image, do you think can we use machine learning to improve or remove the or reduce the degradation by seeing in Earth's atmosphere?
So I think Andres Asensio Ramos and co-authors have been doing this. I think they have a way that instead of doing multi-frame phase diversity blind deconvolution, they have some maybe convolutional network that's that does this. I think it's published. I don't remember the details about what they consider as the ground truth, but I think people are starting to do that, and they certainly use these methods also to denoise the spectral polarimetric data so that for example, especially for the chromospheric signal, it tends to be more noisy, and I think they're using these type of methods to denoise.
Oh, thank you. I didn't know the study yet. I'll check it.
Thank you.
So do you have ideas for you mentioned right at the very end, applying some of the deep learning aspects to the more on the physics side of the problem. I wasn't quite clear on exactly what ideas you have for that or what. Could you just elaborate on that a little bit more?
So for those online, if you didn't hear Lucas's question, he said that at the end of the talk, I sort of alluded to using this deep learning stack for the more physicsy side of the types of questions. Can I elaborate a little bit more? I'll give you $5 later. No. So yeah, for example, so when you do data assimilation, we don't do it much in solar physics actually. People do it for some dynamo models and maybe adapt for the flux transport model. But basically what happens is, let's say you have a state vector, you have a dynamics operator. This is basically your evolution equations. You update your states. Okay, you have an observation operator, which generates the observable data. You have your real observation, and then the difference is called innovation in the data assimilation world. And then they do this analysis step where you use this discrepancy to nudge your state. I mean, in principle, if you do an ensemble method, you also have some uncertainties from your ensemble, and you have your uncertainties in your observations, and then you try to combine those uncertainties too. But let's say you're just updating, you're basically nudging your states, okay?
So that's nudging the entire state vector, for instance, in every single cell in a 3D and HD simulation. Would that be the idea?
Yeah, I mean, you don't have to nudge every single one, but yeah, that's a possibility, right? So yeah, so if you code up your observation operator as a differentiable operator, and you give this innovation, and then your loss function, it doesn't have to be this particular way it's framed, like the difference, straight difference, right? It could be the difference squared, it could be some other loss function that you use. And then you can use the differentiable frameworks to back propagate and correct your state. Yeah, so that's what I'm trying to play around with. Some toy problems that works, but one question is whether it scales to the huge problems, and it would be even better if your M operator could also be coded up in that, but then it takes up a lot of memory. Yeah, so I think there's a lot of possibilities in doing so. But anything that is like a 3D simulation with a lot of degrees of freedom, it becomes very hard. But certainly you can do this for like radiated transfer too, if you want to do your inversions. Yeah.
In the first case study you showed, you said eventually you solve or optimize for the minimum amount of flux transport. How true is that in reality, like with that assumption?
Right. So Georgios Chinsoglu has started a study on this, like using MURAM simulations. Oh, sorry. Let me repeat Shushan's question. In terms of the minimizing the amount of flux transports to get the electric field, how true is that assumption? So Georgios Chinsoglu has started a study of using MURAM simulations as ground truth and then testing the inversions. And yeah, it's let's say I don't have the metrics with me right now, but to a certain extent, you can see that it's sparse, the electric field from the simulation. The reconstruction is not perfect because in the end, I mean, there are different solutions that could fit even the sparse field. But at least it's not space filling. Whereas other electric field inversion methods, including the PDFI, it tend to get these electric field halos. And I would imagine that you probably, we don't have okay. I imagine that you probably have something similar with day for VM, but I think we need a shootout to really evaluate which is better. Yeah, so I think that's ongoing. Anthony Yates, who published this method in 2017, he applied it to sequences of adapt maps, and he solved the inversion for the full adapt map. But that's inconsistent with this assumption of the method, because the adapt maps could have changes in the monopole term, but this is not allowed when you do it on a full map. If you do it on a map that is not the full sphere, then you can have flux moving in and out, and you can have locally unbalanced flux. But so I think what one should do instead of applying this inversion on adapt maps is on just the front side. I'm working on a different project with Mark DeRosa and Carl Henney and the adapt folks in general to compare the flux transport maps. It requires some tuning of this model, like the diffusivities. And the open question is, what actually is the ground truth map that we're aiming for? And I don't know. That's one thing that I want to discuss with Zudong more, and maybe you too, yes. Yeah, if there are no further questions.
All right, if there are no other further
Okay.
if there are no further questions.
Okay. Okay, thanks everyone for joining. We are done.